The next thing we'll look at is the quotient of two complex numbers in polar form. In order to divide two complex numbers in polar form, we simply take and divide the moduli. So it's the moduli of the numerator divided by the moduli of the modulus of the denominator. And then the argument of this quotient is going to be the difference of the two arguments. It's going to be theta 1 minus theta 2 plus I sine theta 1 minus theta 2. In example 5, we're asked to divide the two complex numbers. So we have z1 on top, we have z2 on the bottom. This is going to be equal to, we simply divide those values. 24 divided by 8 would give us 3. And then it's going to be the cosine of the angle from the numerator subtracting the angle from the denominator plus I sine, same thing, the angle from the numerator minus the angle from the denominator. This is going to be 3 times the cosine of 225 plus I sine 225 degrees. This would be our answer in trigonometric form. Let's also convert it to standard form. 225 is going to be an angle that is in quadrant 3 because it's more than 180, but yet it's less than 270. So it's in quadrant 3. In quadrant 3, the reference angle, by the way, would be 45 on this. And then in quadrant 3, we know that the cosine and the sine are negative. And the cosine of 45 is radical 2 over 2. Therefore, the cosine of 225 is going to be negative radical 2 over 2. And the sine would also have a value negative radical 2 over 2. We simply go ahead and distribute, and we get the complex number in standard form. Negative 3 square root of 2 over 2 minus I times 3 square root of 2 over 2. There's one more thing that we're going to look at, which is kind of a application of what would happen if we had like a repeated multiplication. And this is referred to as de Moivre's theorem. De Moivre's theorem tells us how to take an exponent of a complex number written in trigonometric form. It's really nothing more than just an application of our repeated multiplication. But if I have the complex number z written as r times cos theta plus I sine theta, and if I want to raise this to the nth power, the end result is simply a matter of taking the modulus to the nth power, and the argument is going to be the original argument of z multiplied by the exponent n. This is extremely convenient once the exponents get any sizable manner. For example, let's use de Moivre's theorem to find the 12th power of negative 1 plus radical 3i. As it's written, this number would be in standard form, and this would be quite the involved multiplication. If you can imagine what it would look like if you were to try to multiply this thing out without using this theorem, it would be an extremely lengthy and extremely time-consuming multiplication, right? This would say to use the factor negative 1 plus radical 3i 12 times. That's a whole lot of foiling, combining like terms, etc. Let's instead first begin by converting this number into trigonometric form. So our first step is to write z as r cosine theta plus I sine theta. To find r is the square root of a squared plus b squared. So r is going to be equal to the square root of negative 1 squared plus the square root of 3 squared. R is equal to the square root of 1 plus 3. R is equal to the square root of 4, which is going to be equal to 2. The next thing we need to do is find the argument. If we look at z equals -1 plus the square root of 3i, this is a complex number that would be in quadrant 2. So z is in quadrant 2. If we backtrack through the notes just to kind of remind you, if z lies in quadrant 2, then we can find the angle via pi plus the tangent inverse of b over a. So this is going to be pi plus the tangent inverse of b, that's the square root of 3 divided by -1. That is theta equals pi plus the tangent inverse of negative radical 3. We recall that from our inverse trigonometric section, the range of tangent inverse is from -pi/2 to pi/2. The angle between -pi/2 and +pi/2, whose tangent has the value negative radical 3, would be equal to -pi/6. So theta ends up being pi plus -pi/6, which is 5pi/6. So that's our argument. That's going to go here. So z is equal to 2 times the cosine of 5pi/6 plus I sine 5pi/6. From here, we're now going to be able to raise this to the 12th power. If we raise this to the 12th power, that's going to be equal to 2 times the cosine of 5pi/6 plus I sine 5pi/6 to the 12th. This is going to be found by taking the modulus to the 12th power, so it's going to be 2 to the 12th, times the cosine of, now we have to take and multiply the angle on the inside by 12. If we do 12 times 5pi/6, this is going to reduce, 6 goes into itself once, into 12 twice, so we get 2 times 5, it's going to be 10 pi. So it's going to be the cosine of 10 pi plus I sine of 10 pi. From here we can figure this out. 2 to the 12th power is going to be pretty sizable. That's going to be 4,096. 10 pi is actually coterminal to 0. So we get 4,096 times the cosine of 0 plus I sine of 0. And let's write it in standard form. We know that the cosine of 0 is 1, the sine of 0 is 0, and so we get as our answer, z raised to the 12th power ends up just being the real value, 4,096.